Hello kids. Today we're going to go through and start off Unit 2 talking about the structure of the atom itself. In doing so, we know that from Unit 1 that the atom is the smallest form of an element that still retains that element's properties, and that the atom is the basic building block of matter, but it's still made up of other stuff. And the atom itself is made up of protons, neutrons, and electrons. We're going to look at each of those a little further today and look at the properties of each one and how they interact within the atom. Starting off, what is it actually comprised of? Well, essentially the atom is comprised of a nucleus, which is the big center portion of it, and the electron cloud, which is where, as you can guess, electrons are going to be housed. What we're going to get into today is kind of how some of these pictures are both accurate and inaccurate at different times. So we're going to kind of jump back and forth and looking at some of these pictures. Starting us off, we're going to look at the nucleus. It is positively charged, and that's because it has both protons and neutrons in it. Protons happen to be positive. Neutrons happen to be neutral. So when you take that neutral charge, add it to a positive charge, you get an entire entity that is positive. Okay? And essentially the neutrons act like glue, holding the nucleus together. We all know that opposites attract, which means like things repel, and if you've got a whole lot of like things, they really don't want to stick around. So the neutrons help keep them together. Okay? And another thing that we're going to point out is, I'm sure you've seen plenty of textbook pictures that look a whole heck of a lot like this. This is a very, very, very misleading picture of the nucleus. Just because of the sheer size. If we were going through and actually looking at a real atom, you wouldn't be able to see the actual nucleus because it would be so incredibly small. That yellow dot that I just drew right in the middle, right there, just that little guy, would be too big to be the nucleus for this given atom. Okay, so the nucleus is very, 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 almost infinitesimally tiny, and that's something that's kind of incorrectly described throughout most textbooks that you've looked at or most pictures that you've seen. Surrounding the nucleus we have electrons. All right, electrons tend to be negatively charged, and they occupy this area around the nucleus called the electron cloud. Now, why do we call it the cloud? Because basically the electron cloud tells us where electrons are most likely going to be found. It gives us an approximate location. It is not give us an exact position as where they're found. And the reason that we can't get an exact position is because electrons, when they're arranged into shells, which are basically different layers inside the electron cloud, or another word that we call is orbitals, when those happen, we find that the electrons do not move in perfect orbits like you think of when you think about the planets. They're not following this set line. They're not just kind of meandering around in a very rigid path. Instead, they happen to travel in a very unpredictable, random, almost whimsical movement where you never know where one is going to be and how fast it's moving at the same time. You can find one of those two things, you cannot find both. Okay? So the idea that the electrons it's impossible to predict where they're going to be means that the cloud gives us a general location of where the electrons are. We can say with 95% confidence that the electron will be in this given area. Okay, so that's kind of what we mean when we say electron cloud. So big deal here is they're arranged into orbitals, not perfect orbits. Perfect orbit would be a perfect circle. They don't do that. Orbitals are more kind of like they're gonna be around here someplace. We just don't quite know where, when, why, etc. And this is a different drawing of the electron cloud itself. And it kind of shows the idea that here would be one orbital in the middle here, this darker region, and then you get a second orbital that's on the outer region here. Okay. And this gives a better representation, not perfect, but a better representation of the size of the nucleus. Although even this one, way too large. This is way too big to be considered the nucleus for this atom that happens to have 1, 2, 3, 4, 5, 6 electrons, meaning we'd be talking about carbon in this case. Okay. So, moving on, talking about the subatomic particles themselves, this guy kind of summarizes what we've hit so far. Protons are found in the nucleus, and they happen to be positive. Okay, and these guys actually have a specific mass. We call that mass 1 AMU, or 1 atomic mass unit. And realistically, what that means, or what that indicates, is that a proton is going to have the exact same mass as a neutron. Okay, so one proton has the same mass as one neutron. They're both 1 AMU. So neutrons are also found in the nucleus, and they happen to be neutral, so they do not have a charge. Okay, so between the things in the nucleus, kind of the important key that we haven't hit yet is what protons actually do. Protons go through and determine the identity of the element. For instance, if you go through and look at your periodic table, you're going to see a single number that does not have a decimal. Okay? That single number that does not have a decimal, in terms of carbon, you're going to see 6. In terms of chlorine, you're going to see 17. In terms of bromine, you're going to see 35. In terms of hydrogen, you're going to see 1. That single number is basically stating the number of protons in that element. That element has to have that number of protons. Number of neutrons can change, number of electrons can change, but the proton is the specific subatomic particle that defines the element. So we hit the neutrons in the nucleus as well, and that means the only other thing that happens to be in the atom itself, are the electrons. And they are found in the electron cloud, and they happen to be negatively charged. And these guys basically have a very, very, very tiny mass, about 1/2000th the mass of a proton or neutron. So when we think about this, all of the mass of an atom is in the nucleus, basically split between the protons and neutrons. Okay? But all of your volume, so all of that space, because remember the nucleus is so incredibly tiny, the volume of the atom is 99.999999% the electron cloud. So the volume of the atom is the electron cloud. So while you've got this very massive object in the middle, the nucleus, all the space is taken up by those electrons that really don't have any set mass. Okay? So now that we have the basics of the atom itself, we need to look at some of the properties that can be found on the periodic table. I'll switch up to a little different color for that. We've got the atomic number, the mass number, and the average atomic mass, which are things that we're going to hit in the coming pages. First off, what's inside the squares? Every single periodic table will have, or should have, an element name, and my computer doesn't look happy. Should have an atomic number, and that's going to be the number of protons. And when we get into doing atomic charts in the coming weeks, your atomic number and the number of protons are always the same thing. Okay, and I'm not saying it's always 42, but if I give you the atomic number, you know the protons. If I give you the protons, you know the atomic number. And then you're always going to have a symbol, which is going to be 1 or 2 letters, with the first letter always capitalized. If there's a second letter, it's lowercase. And then we're going to go through and have the atomic mass. And this is going to be the average mass of all the different isotopes. And we'll talk about that in a little bit. In terms of the atomic number itself, it's basically the number of protons in the nucleus of the atom. Each element has its own atomic number. You cannot change the atomic number of an element because we can't change from one element to the next. I can't magically go through, much like they figured out with alchemy, change lead into gold by taking away protons or adding protons. Another fun thing that'll help you guys out is in a neutral atom, which unless you're told otherwise, you're going to assume an atom is neutral, the atomic number also happens to be the number of electrons, because if an atom is neutral, that means all the pluses balance out with all the negatives. So all your protons here balance out with your electrons, and that would give you a neutral atom. Okay? So unless I tell you that there is a charge on an atom, you assume it's neutral, which means protons will equal electrons. Okay? So for instance, your atomic number here with hydrogen, we've got 7. 1, 2, 3, 4, 5, 6, 7 positives. With hydrogen we have 1, and with potassium we have 19. Every single potassium atom will have 19 protons. Every hydrogen will have 1 proton. Every nitrogen will have 7 protons. Has to stay that way. When we get into the average atomic mass, basically what we're saying in this case is that the average atomic mass is the average mass for each of the different isotopes found in nature for that element. Okay. Chlorine is kind of one of the easiest to go through and explain because there are only 2 versions of chlorine. Chlorine 35 and chlorine 37. Side note, this is isotope notation. We'll talk about this in a little bit. But anyways, getting back to this, chlorine 35, about 75% of the chlorine in the world is chlorine 35. About 25% of the chlorine in the world is chlorine 37. So if you were to go through and take all of the chlorines, and for a round number we'll go through and we'll say that we've got 100 chlorines, 75 of them are going to be chlorine 35, 25 of them are going to be chlorine 37. And when you average all of those masses out, so add up all those masses, divide by 100, you're going to end up with an average atomic mass that is 35.453 atomic mass units. So what that means is when we look at the periodic table, you're going to see a box that has chlorine in the middle, and down here for the mass, it's going to say 35.453. And again, being chlorine, there's going to be a giant 17 up here in the corner. Okay? And generally that 17 will be nice and big and bolded and whatever. Okay? But this guy is basically going through and talking about the total average mass for every single isotope that's in nature. Okay? When we talk about the mass number, however, we are talking about the mass for a specific isotope. And when I say isotope, I just mean a specific version of that element. So in this case, chlorine 35 is one specific version, and chlorine 37 is one specific version. These are 2 different isotopes of chlorine. So in any case, your mass number is going to end up being the sum of the protons plus the neutrons, which means your mass is basically just what's in the nucleus. And this is, your mass number is just the nucleus. What is in the nucleus? Your protons plus your neutrons. So if I give you the mass number and the neutrons, you should be able to figure out the protons. If I give you the mass number and the protons, you can figure out the neutrons. Or if I give you the protons and the neutrons, you can figure out the mass number. Okay? So how do you find the number of neutrons? Well, I'm going to give you the protons, and you'll be given the mass number. So mass number minus protons gives you neutrons. Okay? So how do I know exactly what the mass number is? We'll tell you one of 2 ways. We're going to go through and we will tell you an isotope notation. So by saying like, hey, this is sodium 23, I just told you what the specific mass number is. Or the other option is if I name it. So in this case, and I know you can't see the bottom of the screen, but sodium 23. I just told you that the specific sodium we are dealing with has 23 as a mass. And this guy has 23 as a mass. Okay, so I'm going to tell you exactly what you're expected to know in terms of mass. And the only thing that we've got to do here is kind of figure out what some of the elemental parts are. So this should be pretty darn easy, and this is where your handy-dandy periodic table comes into play. But if I have boron, knowing that I've got an 11 here, I know that my atomic number for boron happens to be 5, which means I have 5 protons, because these are always the same. I know that my neutrons, I'm going to wait a second to figure that out, because my mass, remember this guy was my mass. Okay, so this guy is going to be 11. And that means my neutrons are just the 11 minus the 5 to give me 6. So my atomic number and protons are always the same. Mass number is told to me, or the other way is protons plus neutrons. And my neutrons are just mass number minus protons. So what I'd like you to take a second to do is give it a pause, see if you can fill in the rest of it, and I'll give you some answers in just a second. But pause it, seriously, and do it. So I assume you took a second to work your way through. We got about 20 seconds left, so I don't have the time to go through and work through them with you, so I can go ahead and kick you some answers. The only one that I can tell you is this last one. Because I only told you neutrons, you can't figure out the rest. I need to tell you either a symbol or an atomic number or protons or a mass or something, you can't figure something out based on neutrons, because neutron numbers can change. Anyways, we'll do it again later, kids.